So here is our discussion of section 4.1 from our calculus book. It's about extreme values of functions. We'll start with the definition. We're going to say that if a function, we have some function on a particular domain D. Let's say there's a C, by the way, that C is in the domain D, and we say f of C is an absolute maximum on that domain if and only if it is larger than or equal to all the other values from that function on that domain. All right? Now, let's see, and the minimum function got the same idea. F of C is a minimum, absolute minimum, if it's smaller than or equal to all the values that f of x produces while x is in the domain. So let's say we talk about a known function, the function y is equal to x squared. There it is. Now, we want to talk about the absolute maximum. On the domain from negative infinity, that's x is negative infinity, all the way to positive infinity. Okay? Absolute maximum. Well, this is going up forever. This is going up forever. We might clearly say that there is no absolute maximum. So, for example, if you were to say, I can name an absolute maximum, it's f of 10. Here's 10, and here's f of 10. I would simply say, no, I can produce a number that doesn't satisfy that it's bigger than all the other values. In other words, I could say, you know what? It's bigger, f of 11. It's going to be bigger. And we could play that game all day long. You name a value, I name a position in which the function produces an even bigger value. No absolute maximum on the interval from negative infinity to positive infinity. But let's say we change the domain to open at 0 and closed, I'll change the thing here, and closed at 2. I can clearly say that f of 2, which is equal to 4, is an absolute max. Why? Because you cannot name for me a value x in this domain which produces a bigger value. And even if we include the low end, we can still say the absolute max is f of 2, which is equal to 4. But what if we end up with a special case? Closed at the low end, but open at the high end, open at 2. You say, oh, I don't know, maybe f of 1.9 is the absolute max. You propose this. And I said, well, I don't know. I think I can produce a value that's bigger than that, like f of 1.99. Great. You say, well, then how about f of 1.99? That could be the absolute max. And I said, well, no, I could produce a bigger value than that, 1.999. And then you said, well, I got you beat next time. I'm going to say, I got a value and it's f of 1.9 repeating. And I say, yeah, that would be bigger, but that's not in the domain because 1.9 repeating is exactly the same as the number 2. Let's do a little quick proof of that. Let's say x is equal to 1.9 repeating. Let's say 10x is equal to 19.9 repeating. And if I subtract equation 1 from equation 2, I end up getting that 9 is equal to, 9x is equal to 18. Divide both sides by 9. X is equal to 2. So x is equal to 1.9 repeating, and it's equal to 2 because 1.9 repeating and 2 are the same number. So it ends up that with this open top end, there is no f of c that you can produce for me, that I can't produce another number that's bigger than it and still's in the domain. We say, even though, again, we're looking at this graph, there is no absolute max in this situation. So how can we summarize something like this? Well, our summary is in the form of this thing called the extreme value function, sometimes abbreviated as the EVT. And it says, as all theorems do, if some condition is met, here's our condition, there's a consequence. Okay, the condition here is that we have a continuous function on a closed interval. The consequence is there must be an absolute max and an absolute min for that function on that closed interval. Now, there may be some variations about where that absolute max and absolute min occur. For example, in this graph number 1, the absolute max occurs in the interior of the domain. The absolute min occurs also in the interior. But in graph 2, could very well be that the absolute max occurs on an endpoint and the absolute min occurs at an endpoint. Or the min is at an endpoint and the max is in the interior, like we see in graph 3. Or, like we see in graph 4, the min is in the interior and the max is on an endpoint. Regardless, continuous functions, closed interval, conclusion, there must be an absolute min and an absolute max. Now, that's a nice thing to know. Let's go on to the next thing, and that is we are going to talk about being in a domain and talking about what's called a local minimum, or sometimes also called a relative maximum or relative minimum. Now, in this case, it says something is referred to as a local max or local min. I'm going to paraphrase here. If it's the largest value for the function for all the values near it. Near it. That's vague. Okay. The more rigorous mathematical phrasing of this is that it's larger than any other value for some open interval containing the value where we say the local max or local min is. So, for example, here is a local maximum. This value, this f of c value, is bigger than all of the values for this function in, let's say, an open interval that's about this big. Now, I could make it smaller if I need to, but it's an open interval that contains c. And you can see that all of the values are less than or equal to that value. Okay, local minimums and local max may occur at endpoints. Okay, it says if you're at an endpoint, then you have a half open interval. So that contains A. Well, there we go. Start at A and go someplace forward. Yep, this value, f of A, is smaller than all of the values in that half open interval. This value, f of E, the height of this curve here, that value is smaller than all of the values for the function in this interval that I just drew containing E. You said, well, what if you went and said the open interval went all the way down to here? It doesn't say it has to be the smallest value for all open intervals. it needs to be open for some open intervals. If I can draw it and it's the smallest, then it's a local min. All right. Now, that's all well and good. Please note, none of this has any calculus in it. You know, I talked about being the largest value, the smallest value, and never did I refer to taking a derivative, because we do not define extreme values based on derivatives. What we are going to do is say one way to find extreme values is to use calculus. So here's a theorem for extreme values, especially local extreme values. It says, if a function has a local max or local min at some interior point C, and if f prime at C exists, if the derivative exists there, then it has to be that f prime of C is equal to 0. It doesn't say, what it doesn't say is that if f prime of equals to 0, then it's a local max or min. It just says if there is a local max or min and the derivative's there, it's equal to 0. Let me summarize what we're going to use this for. A good place to look for a local max or a local min is where the derivative function is equal to 0. Again, it doesn't guarantee we'll find one, but if it happens to be a place where they hang around. All right? Now, you say, that's great. I can imagine a function like our y equals x squared function. There's that local minimum. And indeed, at that local minimum, f prime is equal to 0. But you can also imagine functions like the absolute value function, where there's a local minimum, but the derivative doesn't exist. So maybe we can extend this and say, or places where f prime of x does not exist. And that's exactly what we're going to do. And we're going to define those places where the derivative is 0 or the derivative is undefined. We're going to define them as this thing called a critical point. A critical point for some function is a place where the derivative is 0 or where the derivative doesn't exist. And again, why do we care? Because it's good place to look for extremes, maximums and mins. Right? That's all we're saying. If we're going to go look for something, why don't we look in the places we're most likely to find it? All right. So example, let's think about the absolute max and the absolute min of this function on this interval. Wait, this function, I wonder, is this function continuous? Answer, yes. And if it's continuous, we are guaranteed that this function will have an absolute max and an absolute min. Where to look for those absolute maxes and mins? Where to look? Answer, we could look at endpoints, because as we saw from that first set of graphs, that absolute maxes and mins can occur at endpoints. We can also look at critical points. Places where the derivative is equal to 0 or where the derivative is undefined. So let's let's start this. Let's take a look at let's take a look at the critical points. If I take the derivative of that function, I bring the power down, so I get 2/3 x to the negative 1/3, which can be rewritten as 2/3 times the cube root of x. Now, f prime of x equals 0 nowhere, but f prime is undefined at x equals 0. So if I had to make a list for critical points, x equals 0 is one place. What about the endpoints? X is equal to -2 and x is equal to 3 are endpoints. And as far as I'm concerned, those are the only places where we would be possible to find these absolute extremes. So I might say, hey, I wonder what f of 0 is. What is this functional value at this proposed location where there might be an extreme? Well, 0 to the 2/3, 0. What about f of -2? That'd be -2 to the 2/3. So that would be something like well, it would be positive, whatever it is. And it would be, yeah, +2 to the 2/3. And then if I said f of 3, I get 3 to the 2/3. Okay. It ends up, if we do this ends up being the cube root of 9. This one ends up being the cube root of 4, and this one's largest. Which means it is the location of the absolute, it is the absolute maximum. It's the largest value of all the possible values that could be extremes. This is the smallest. So this must be the absolute min, meaning that 0 is the smallest value that function produces on that interval. All right. And this is, by the way, this whole thing is called the closed interval method. All right. That was fun. How about we try this again? Here's a function. We're trying to find extreme values. So we're looking for local maxes and mins because it didn't say absolute. All right. Where should we look? By the way, is this continuous, this function? What is the limit as x approaches 1 from the negative side? That would be 5 minus 2, not x, 2 times 1 squared, that's 3. What is the limit as x approaches 1 from the positive side? That would be 1 plus 2, which is 3. Yeah, no matter whether we come at it from the right or the left, it's equal to 3. It's continuous. All right. So where could we find the extreme values? I'd like to know, where is f prime 0, for example? Well, let's find out what the f prime of this piecewise function is. When x is greater than 1, I take the derivative of this, I get 1. When x is less than, or I'll say less than 1, then this expression produces 5 minus 4x. Okay, I can clearly see for x greater than 1, there's no place where it's equal to 0. I can clearly see that 5 minus 4x, when is it equal to 0? When 5 is equal to 4x, when x is equal to 5/4. Wait, but 5/4 is not less than 1. So this value doesn't fit that condition. So that's not a place. There are no places where this this function has a zero derivative. Is there a place where the function's undefined? Sorry, where the derivative is undefined? Well, the left-hand derivative, the one that's coming in from x values being lower, it's 5 minus 4 times 1, which is 1. The right-hand derivative is 1. Oh, those derivatives equal. There's a derivative at that place, and its derivative is 1. There are no critical values here. That means that this function, there's no place where there could be a relative max or a relative min. You know what? Let's take a look at this visually and see if we can make it make sense from that perspective. I'm going to go ahead and we're going to take this function, this piecewise function, and we're going to put it in our graphing calculator. Come on, graphing calculator, start up. There we go. I'm going to add a graph. I am going to go to this menu called the templates menu. I'm going to go up to the top row where they give me a chance to write a piecewise function. And that piecewise function, as we said before, 5 minus 2x, 5 minus 2, I think is x squared. Just double check that. Yeah. And that was when x was, and that less than or equal to sign can be found above the equal sign. So a control equals, and there's less than or equal to right there, less than or equal to 1. We will go down here. And then the other one was x plus 2. And this is when x is control equals greater than 1. And then I hit enter. Well, that's not what I expected. I said that 5/4 is not less than 1. And I'm right there. So what did I do? I took the derivative, I got that, I set it equal to 0, brought the 4x over, and I got 4 5/4. Oh, I see what I did now. You see where the error I made? The derivative of 5 minus 2x squared, the derivative of 5 is 0. So this is negative 4x. When does that equal to 0? When x is equal to 0. Ah, so at x equals 0, f of 0, f prime of 0 is equal to 0. Therefore, f of 0 is a potential relative maximum, which we'll call a relative extreme. Extreme, singular. All right. And when we take a look at that graph, indeed, do we see that relative maximum? Sure. Okay. It ends up being a relative maximum. Great. Okay. And there's no other places where it's the slope is undefined. Now I have this other thing. I got this thing where did I screw this up? Look at, that's clearly a corner there. There seems to be a lack of a derivative there. How did I get the two derivatives equal to each other? Oh, back to that same old mistake. That 5 should be a big old 0. The left-hand derivative is -4. The right-hand derivative is 1. So f of 1 is a potential relative extreme. And what do we see? What do we see from that graph? Yeah, not only is the potential relative extreme, it is a relative minimum. It is the lowest point for all the points near it. Okay. All righty. So one mistake that cost us two correct ideas. All right. Last problem. Find the extreme values for this function. Now, if you don't mind, I'm going to rewrite this function. I'll rewrite it as 9 minus x squared to the 1/2 power. So f prime is equal to 1/2 times 9 minus x squared to the negative 1/2 power, and then derivative of the inside, negative 2x. I get negative 2x over 2 square root 9 minus x squared. These 2's cancel. How about just negative x over 9 minus x squared? So I got the derivative. Does the derivative equal 0 any place? Sure does. It equals 0 when x is 0, because I get my numerator to be 0, but my denominator is non-zero. So there's a place that may be interesting to us. Okay, what's the domain of this function? Is it an infinite domain, or is it limited? Is it a closed domain, or is it open? Well, let's see. What's going to keep this function or this derivative from existing? Oh, square root. Things inside the square root have to be greater than or equal to 0. Or 9 has to be greater than or equal to x squared. Okay, 9 has to be greater than or equal to x squared. So if I draw the x squared function, where does that happen? Where's the area in which the curve is less than 9? Ah, between -3 and +3. So the domain of this function is from closed 3 to open 3, or from closed -3 to closed +3, which means those are endpoints. And those are also potential places of maximum and minimum behavior. So what do we think we have here if we were to graph that out? Looking at 0, looking at -3, looking at +3, those locations in which the extreme behaviors may exist. Well, let's take a look at the function. I'm going to control doc, which is going to add a page. I'm going to let that be a graphing page. I'm going to go control division, so I can put in this fraction, which represents that function. I'm going to hit enter. And what do we see? Well, it looks like at 0, looks like we have a relative minimum. So f of 0 is a relative minimum. At least it looks that way on the graph. What about f of -3? What did we see? Well, this function is, oh my gosh, I made another mistake. It is true that for the square root to be valid, it could be the radicand, the thing I'm going to needs to be greater than or equal to. But since this is the denominator, it must be strictly greater than 0. So we've got these two places at the end here that are open. The domain is not closed. It's open. There is no function value at -3. There is no function value at 3. So the only thing we have going on because of those open endpoints is that there's only a relative minimum. There is no relative or absolute maximum. All right. Oh, by the way, this f of 0 is not only a relative minimum, it's an absolute minimum as well. No absolute maximums on this function.